Hi everyone. In the previous lecture, let us recall what we looked at. So, recall from the previous lecture. So we looked at this cost function properties. We designed the simplest gradient descent algorithm. And we looked at how we arrived at this gradient descent algorithm. Especially, we focused on the core of the algorithm, the iterative step. Omega tau plus 1, omega tau minus eta nabla E of omega tau. Right? This was the core of the gradient descent algorithm. Today what we are going to do in this lecture, what we are going to do is look at this iterative step in a different way and then arrive at variants of the gradient descent algorithm. So before we proceed, there's one thing that we want to look at when we are studying the gradient descent algorithm, especially the simplest gradient descent algorithm that we looked at in the previous lecture. So what was happening was there were chances that we could actually land in one of the local minimas and get stuck there, the algorithm, especially when you look at this iterative step. The nabla E of omega tau, which is the gradient of E at omega tau, this would become 0 at the local minima, and then as you can see, this particular term is going to become 0 at that point, and then the iterative step is always going to give the same value of omega tau vector, right. So, we could get stuck at the local minima. So, what is one way of looking at this differently, or what is one way of avoiding this kind of getting stuck at local minima? So, one way of doing that, what is done in practice generally, is that you do this entire simple the gradient descent algorithm by starting at multiple random points which are spread across the parametric space. So, you start at multiple points and then continue with this procedure and wait for the convergence of this procedure. The convergence meaning when in the iterative step you arrive at one particular parameter and then the iterative step stops changing it significantly, and you do this for multiple of these starting points, which is omega 0, and then when you do this and then you arrive at each one of those, you arrive at one of the local minima. What you do is you are going to compare the cost function value at each one of those minima and then choose the one which is the lowest. So, what does this imply computationally? The more random points you take and the more times you run these gradient descent algorithms at each one of these random points, starting from each one of these random points, you have more local minima that you are finding, and then you can evaluate them and then get those parameters which minimize the cost function greatly, right. Meaning the more random initializations that you do, the closer you the higher the chance that you have to get the global minima. So, that is what happens. But again, so this is a trade off. If you are running gradient descent algorithm multiple times, then again you are increasing the computational burden on the computer or the system. So, that is something that we want to keep in mind. Okay, now let me write down the cost function for the least square so that we can concretize things, look at the cost function more closely again. So, E of omega in case of a least square cost function applied on the example that we took yesterday, on the example that we took in the previous lecture of the regression model. So, E of omega was summation I is equal to 1 to n yi minus Ti square. So, yi was the model that we were working on, trying to fit to the data, and Ti was the true target variables from the training data. So, when we look at this, what we can observe here is, like we mentioned again in the last lecture, this cost function has the whole training data embedded in its form, right. This has the whole training data embedded in its form, which means what? Supposing you have in this problem, supposing you have a huge amount of training data, to make any single computation of this cost function, it is going to involve that entire data to make the computation and arrive at what is the function value E of omega at that particular omega cost function value. So, this is what can potentially form a computational bottleneck, especially if you have huge amounts of data, and especially if you are working with complex hierarchical models like we mentioned in the last lecture, like the neural networks and so on and so forth. It is going to become extremely computationally intensive, not just for calculating E of omega, it is also going to become computationally expensive to calculate nabla E of omega or the gradient of E at omega. So, we want as much as possible to reduce the computational burden, right. So, how do we look at this? How can we look at this cost function differently? One thing that you can notice here is that within, if you look at the summation over each one of the training samples, each part of this summation, right, each component of this summation has the same kind of form, least square, right. So, we can supposing we take this as say E tilde I, let us denote it by E tilde I, okay, E tilde I of omega. So, supposing we look at this way, okay, we look at this cost function in this way, E of omega is summation I is equal to 1 to n Ei hat of omega. So, supposing we look at it this way, and then we know that gradient distributes across a summation, right. So, nabla E of omega, if we take the gradient of this function, gradient distributes across the sum. So, this is the same as summation I equal to 1 to n nabla Ei tilde of omega. So, this is the clue, for us to modify our iterative step. So, how do we do that? So, in the iterative step, in the simplest gradient descent, omega tau plus 1, omega tau minus eta, instead of taking nabla E of omega tau, we can randomly pick a point, we can randomly pick a training point, calculate the gradient nabla Ei tilde of omega at that particular training point, the ith training point, and then use this instead of nabla E of omega. So, this approximation, because we are randomly randomly picking a particular training sample and then calculating the gradient Ei tilde of omega and approximating the overall gradient of the cost function, there is an introduced stochasticity, or the randomness has been introduced by randomly picking a particular training point, and therefore, this is what is popularly called as the stochastic gradient descent algorithm. The stochastic gradient descent algorithm. So, how did we arrive at this? Why did we arrive at this stochastic gradient descent algorithm? Because we faced the computational bottleneck of having to compute over the entire training data, because in many of the currently functional models out there, most of these AI and ML models are working on something called as big data, meaning you have huge amounts of data and lots and lots of computation, because you have to work on that much of number crunching because of the sheer large size of data. And adding another complexity to the same thing is like working on parametric models with millions and billions of parameters and so on and so forth. So, at every step at every level, you want computations to be as light as possible. That is one reason. And the second reason is again interesting, which is the introduction of stochasticity here. So, now I will connect this with what we just discussed before. So, we said that we would randomly initialize the starting points of the simplest gradient descent algorithm and perform the simplest gradient descent algorithm in each one of the, starting from each one of those random points, and then arrive at many of the minima, and then find the least one, right? Least one that minimizes the cost function, the one that minimizes the cost function the most. So, that is what we did, we thought there. And here you can see that randomness is being introduced in this iterative step itself, because you are randomly picking the training data. So, this also gives you that advantage of not being stuck, that the advantage of being stuck at a local minima at a lower probability. And now you can also scale this algorithm to a large set. You can scale this algorithm to a model that is built on large training data as well. So, this is the stochastic gradient descent algorithm. So, there is another way to look at the iterative step. So, what we will do now is we will slightly more abstract the iterative step. So, what we will do is, so if you look at the iterative step, omega tau plus 1 was the next point that you were arriving at, starting from the point omega tau. Sorry, this is not omega tau plus 1, but omega tau, and then taking a step. So, this is the simplest gradient descent algorithm, and then you are taking a step coming from this step size, right. So, this I can write in another way. So, I will write it in brackets, because so that you can keep in mind this way. So, this was the step size, or the difference between omega tau plus 1 and omega tau. So, this was the step size. So, if you denote this by delta omega tau, this is what the abstraction looks like. Right. So, so we have come a little more abstractly. So, why this abstraction is because this is from where you can lead to different variants of the gradient descent. So, we have already looked at three variants right now. So, number 1, where delta omega tau was just this much, nabla E of omega tau, right. This was the case of gradient descent without the idea of learning parameter or learning rate. So, we were not scaling the step size with the learning rate at all. So, this is one, and then we looked at the simplest gradient descent in practice, which is with the learning rate, right. So, this was the simplest gradient descent, and we also just now looked at something very interesting, which was the stochastic gradient descent, where the step size was. So, in fact, here the gradient was actually approximated. the gradient itself was approximated. So, this was eta del E hat of omega tau, where this was picked randomly. So, how do I write that? Let me just mention it in bracket. Pick randomly. So, we have already looked at 3 variants of the gradient descent algorithm, and all of these variants you can see is in the step size. So, how we take this is where you get new kinds of gradient descent or variants of the gradient descent algorithm. So, here what we can do differently now is one thing to notice here is entirely we are only using the gradient information of the cost function, right. Because we are using only the gradient information of the cost function, these are also called as the first order methods. These are called as first order methods. First order methods. So, now what we are going to look at is something quite interesting. So, you have come across the Taylor series approximation for the multivariate clays in the previous lectures. Professor Alan has worked on all this, and he has introduced all of this to you. So, we are going to borrow that idea. We are going to take that idea and then, so let's make the Taylor series approximation at say some omega hat. So, let's make the second order Taylor series approximation at omega hat. So, at omega hat. So, what is the second order Taylor series approximation? So, E of if you recall, E of omega is equal to E of for sufficiently close. So, for sufficiently close omega closer to omega hat, we have this equation holding true, E of omega hat plus omega minus omega hat transpose nabla E, the gradient information, the first order approximation part, E of omega hat plus the second order part, right. We are doing the second order Taylor series expansion. So, omega minus omega hat transpose the Hessian omega minus omega hat, right. So, this is the second order, let me write that down, second order multivariate, second order multivariate Taylor series approximation. Now, let us look at this slightly differently. So, E of omega minus E of omega hat is approximately omega minus omega hat transpose nabla E of omega hat plus half of omega minus omega hat transpose Hessian operated on omega minus omega hat. So, this equation, if you look at it closely, if you minimize E of omega minus E of omega hat with respect to del omega, if you are minimizing this function, let us say E of omega minus E of omega hat, if you are going to minimize this, it is equivalent to minimizing E of omega. Can you see that? Can you see as to why it is like that? Precisely because E of omega hat is constant, because omega hat is fixed, right. So, when you differentiate this is going to be equal to 0. So, minimizing E of omega minus E of omega hat, because this part is a constant, is equivalent to minimizing E of omega. But now what are we looking at? We are looking at something interesting. We are going to try to minimize this with respect to omega minus omega hat. If we denote this as delta omega like we did when we generalized and made this abstract, if we denote this as delta omega, what we are going to do is now to minimize this with respect to delta omega, this is what it is going to look like. This is what we are going to minimize. This is also effectively minimizing E of omega, right? So if I have to take the gradient of this and equate it to 0, what does that mean? So let me go to the next page. So yeah, so rewriting that, nabla with respect to delta omega, E of omega minus E of omega hat is equal to 0, like we are minimizing that, right? So this is going to give us possible minimas with respect minimas for delta omega, right? So what does this look like? If you recall the second order Taylor approximation, so this was approximately so I'm already replacing omega minus omega omega hat with delta omega. I'm already replacing that with this symbol, transpose nabla E omega hat plus half of delta omega transpose Hessian omega hat at omega hat operated on delta omega. This is equal to 0, right? And what does this look like with respect to delta omega is what you are doing. So the first term just becomes the gradient of E omega hat because that is a constant. Then the second half of the term becomes the Hessian operator on delta omega, and this is going to be equal to 0. In other words, half of H omega at delta omega is equal to minus del E omega hat, or the Hessian is a in case of where we have the minima, or when we have arrived at the local minima, the Hessian at omega hat is invertible here. So we have minus E omega hat 2 times and H omega hat inverse, right? So let me write that more clearly. So delta omega, which is actually omega minus omega hat, which is minus 2 times H omega hat inverse nabla E omega hat. Now this here, supposing omega hat, now we can look at omega hat as omega tau, right, and omega as omega tau plus 1. So what are we trying to do? We are trying to look at the iterative step in a different way, and we want to arrive at how to take the step size, right? Now this gives us a particular way of arriving at the step size. So omega tau plus 1 is equal to omega tau minus 2 times the Hessian inverse nabla E omega hat. Now here if you see closely, not only are you using the gradient information, but alongside it you are also using the Hessian information at omega tau, right? So here, sorry, omega, so I made a mistake here in notation. So omega hat is actually omega tau now, omega tau, omega tau. So this is again omega tau. Oops, sorry. Omega tau, omega tau. So here if you look at it in the iterative step, you have the Hessian, which is being Hessian information at omega tau being used at the step where you are, and then you also have the gradient information that is being used at the step where you are to take the next step, and therefore this is also called as this is one method of the second order Newton methods. So, this is the second order Newton methods that has been used to arrive at the step. What is the next step? Basically the step size. So, this is our fourth variant of the gradient descent algorithms that we are looking at, where the step size delta omega is actually given by -2 h omega tau inverse del E omega tau. So, this is a Newton method or second order methods. So, you would have come across many of these packages wherein you would have come across something called the BFGS algorithm. So, BFGS algorithm is an example of Newton method, except with there is one difference in that, wherein even the Hessian which is calculated here is actually very computationally expensive, and therefore, they also approximate the Hessian. So, iteratively at every iterative step they are approximating the Hessian, and Hessian is also getting updated in the same iteration. So, that is the only difference, and this difference is called, so this difference is leads us to call these methods as quasi-Newton methods, where one of the example is BFGS. So, they are called as the quasi-Newton methods, and LBFGS is again a quasi-Newton method, but it just has different ways of looking at the different ways of using the memory and all that kind of computational aspect. So, apart from that, BFGS or LBFGS are also are examples of the quasi-Newton methods which are built on the second order Newton methods. So, there are some more variations in those algorithms compared to the one that we have arrived at today in this lecture. So, so these are the variants of the gradient descent algorithm. So, this brings us down to the end of looking at the gradient descent algorithms. So, we can summarize this entire lecture, what we have looked at. So, in these two lectures we started with the cost function, and we understood that minimizing the cost function was actually the learning part of the machine learning algorithms. We started with that, we understood the properties of the cost function. What we did was we took the those properties to our advantage, came up with the simplest form of the gradient descent algorithm, wherein we actually isolated the core of the entire gradient descent algorithm, which is the iterative step, and we started looking at the iterative step in different ways to give us different kinds of advantages. So, beginning with the computational advantage, when we were looking at trying to reduce a lot of computations, we arrived at the stochastic gradient descent. It also gave us the added advantage that stochasticity was introduced, which was minimizing our probability of being stuck at a local minima. So, from there we summarized the first order methods, wherein we looked at how changing the step size little bit or gradually or in different ways was actually giving us different variants of the first order gradient methods. Then we actually looked at the Taylor series itself in a different fashion. We looked at the iterative. We arrived at the iterative step by actually taking the gradient of the second order or Taylor series approximation at omega hat, and then we arrived at a particular step size, which was also taking information from the Hessian at that point, and then we finally looked at the second order Newton method in this case, and then we also talked about what is BFGS, which is popularly used, and what are quasi-Newton methods. So, this brings us to the end of the gradient descent algorithms, and we have studied currently some of the most widely, popularly and most powerful tools which are used across problems wherever machine learning and optimization is being applied. Thank you for listening to this lecture.